Hello everyone, today we're going to be going over scientific notation. So here's the joke of the day. How does a dolphin make bread? Okay, so for regular notation, this is the standard way we write numbers. So just like we write a number, for example, like 870,000. And then scientific notation is a way it's like a shorthanded way of writing really large or small numbers. In scientific notation, it should say the number is a written product of two numbers. So it would be something like this, like 2.7 times 10 to the 6th. Okay, so let's look at some examples now. So this is just like a visual as well of what scientific notation looks like. So you can see here that the first factor, it's always going to be a number between 1 and 10, and it may or may not have a decimal. And then the second factor, it's always a power of 10. So the power of the exponent tells you how many places to move the decimal point. The sign of the exponent tells you which direction to move it. So if it's positive, you're going to move the decimal to the right. And then if it's negative, you're going to move the decimal to the left. So if the exponent is greater than 1, that means that it's a big number. If it's less than 0, that means it's a smaller number. Okay, so let's look at some examples. So it says convert the following from scientific notation into regular notation. So here we have 2.47. I'm going to write in a different color just so you guys can see it better. And so we're going to move that decimal point 3 to the left. Two and 3. And remember, in front of this 2, there's like some invisible zeros that we can write. Same with after the 7, we could write like some invisible zeros. And so that new decimal point is going to go right here. And so the answer would be 0.00247. And so now the second one we have 9.3 times 10 to the 7th. So that means that we're going to move the decimal point 7 to the right. So I'm just going to write out, honestly, a bunch of zeros. So the original decimal is right here, 9.3. And we're moving it 7 to the right. So I'm just going to count over 7. So 1, 2, 3, 4, 5, 6, 7. Oop. I don't know why I did that. Let me try again. 1, 2, 3, 4, 5, 6, 7. And so the new answer is going to be 93000. Let's count how many zeros. 1, 2, 3, 4, 5, 6 zeros. And so this will be 93 million. Okay, so then we have 8.5 times 10 to the negative 5th. So same thing, let me just write out the 8 and the 5. And then I'm going to write some zeros here in the front. And then I'm going to go ahead and I'm going to again move the decimal 5 back. Again, since it's negative, we're moving it back. 1, 2, 3, 4, and oh my gosh, I don't know why it keeps doing that. 1, 2, 3, 4, and 5. And so the new decimal is going to be right here. Let's add another 0 here. And so our new number is 0.00085. Okay, so now we're going to convert some of the examples from regular notation to scientific notation. So here, I'm going to look at how I can move the decimal forward or back to make the first factor in between 1 and 10. So in this case, in number 1, I'm going to move the decimal 1, 2, 3 to the right. So then we'll have 2.4 times 10. And even though we moved it to the right, the exponent is going to be negative because it's a smaller number. So in this case, it's going to be -3. So even though it's moving to the right, it's going to be negative. And then vice versa, like let's look at the second one. So the decimal is invisible right here, and we're going to move 1, 2, 3 to the left. And so we'll have 5.6 times 10 to the, and it's also going to be 10 to the third, but it's going to be positive because we're talking about a bigger number. So you can see, even though it's positive, we move to the left in this case. And so let's look at the next example as well. So we're going to move 1, 2 to the left. And then, so you could write this number as 5.6, or you could write it as 5.604. 04 is not a significant decimal per se, but in this case, the 6.9375, that's something you might want to write out. So I'll just write it out. So 6.9375 times 10 to the, we moved 2 to the left. And since we moved to the left, the exponent is going to be positive 2 to the second. Okay, so now we're going to look at some real-world examples. So it says, use the table to answer questions about different celestial bodies in a hypothetical star system. So the first question says, which celestial body is least numerous? Estimate how many times more asteroids there are. So the least numerous, we can see here, if we go to the number in the system, we're looking for the lowest number. And immediately I see here that the stars have a 0 exponent. And there's no negative exponents here. And the planets also have a 0 exponent, but the 8 is going to be bigger than the 1, right? So then the stars is the least numerous. And then it says, estimate how many times more asteroids there are. So to find this, we're going to do division. We're going to take the asteroids and we're going to divide it by the number of stars. So we'll do 1 times 10 to the 6th. That's how many asteroids there are, divided by 1 times 10 to the 0. And so since the ones are the same, it's just going to stay as 1. And then we'll subtract the exponents since we're dividing according to the quotient rule. And so that would be 1 times 10 to the 6. So that means there's going to be 1 million times more asteroids than stars. Okay, so looking at the second question, it says, which celestial body is least massive? And then it says, estimate how many times more massive a planet is. So if we look to see the least massive. Mass is over here. So I'm going to look at which has the smallest exponent. I'm also looking for any negatives. I see here space dust is the only negative. So space dust is the least massive. And then it says estimate how many times more massive a planet is. So to figure this out, we're going to again do division. So we'll look at the planets, and you can see the planet mass is 6 times 10 to the 24th. So we're going to do 6 times 10 to the 24th divided by 1 times 10 to the negative 9th. And so 6 divided by 1 is just 6. And then with the quotient rule, we subtract the exponents. And so this is going to be 24 minus negative 9. Since it's two negatives, it's going to be a positive. 24 plus 9 is going to be 33. So the planets are 6 times 10 to the 33rd power. More massive than the space dust. And this number adds up to an octillion, which is a really, really high number. It's just really, really large. So this is like a great example of why we would use scientific notation. Because no one really talks about octillion. Okay, looking at the next question, number 3. Which is more massive, the total mass of all the moons or the total mass of all the comets? About how many times more massive is it? And so we can look at the total mass of the moons. Here's the mass of just one body. So it's 7 times 10 to the 22nd. And then here we see that these are the numbers that they have in the system. That's how many moons there are. So we're going to multiply those to get the total mass of all the moons. And so 2 times 7 is going to give me 14 times 10 to the 2nd, and the 22 I'm going to add. Because remember, according to the product rule, when I multiply exponents, I add them. We need to convert this, though, to 1.4. So that's going to add 110 to the decimal, so it's going to be, 110 to the exponent, so it's going to be 10 to the 25th. And so now we need to look at the total mass of the comets. And so the total mass of the comets, we're going to do the same thing. 1 times 10 to the 4th times 1 times 10 to the 13th. And so 1 times 1 is 1 times 10. And then 4 plus 13 is going to give us 17. And then now we need to compare them and see which one is more massive. And so I'm going to take the larger exponent and divide it by the smaller exponent. Typically when I have a larger exponent, that always means that it's going to be bigger. And so I'm just going to do 1.4 times 10 to the 25th divided by 1 times 10 to the 17th. And that's going to leave me 1.4 divided by 1 is just 1.4 times 10 to the 25 minus 17 is going to be 8. And so that means that it's 140 million times more massive. And I'm running out of room, and also I'm running out of a little bit of time, so I'm just gonna cancel number 4. We're not gonna answer that question. And then back to the joke of the day. So the joke of the day is, how does a dolphin make bread? And the answer is with all porpoise flour. Alrighty, thank you all for watching. I hope you enjoyed.